right, let's bring it home. Let's graph these two things. 1, 2, y, x. Now, this thing is a straight line, y-intercept 2. Y-intercept 2. It's got a gradient of 2 on 3, so that would be 3 on 3, so 2 on 3 would be like that. So let's draw a line, kind of looks like that. Sure, so make sure it goes through the point. Okay, that's that. Now, we've got a parabola with the squared. It's raised 1, so its vertex is at 1, and it's been moved to the right, negative, 1. So 1, 1, it's here. Let's call that 1, 1. And it's an upwards parabola. Okay, I'm just going to be careful with these cuts. So it's got a y-intercept of, 0, 1, so 1 squared plus 1. Okay, it's got a y-intercept of 2, which means it cuts through this point. Okay, so you just got to be careful that you draw it correctly, because I anticipate the next one's going to have something to do with calculus. Oh, look at that. Okay, so find the area between the two curves. So what we're doing here, let me go to my picture. That is y equals 2 on 3x plus 2, and this is y equals x plus 1. So what you'll notice is this graph is on top of this graph. So in order to find this area, you've got to do this integral, which will give me all of this, and I take away this integral, which will give me this. Okay, so I've got to do the integral of, and I'll use brackets, 2 on 3x plus 2 minus x minus 1 squared plus 1. Whoops, excuse me. Okay, so that'll give me the area. Now, I need to be able to do it. I hate that. So I need to find my area between this value and this value. So in other words, I need to kind of know what this value is. So that's something I need to do. The way that I'm going to do that, so I need some more working out room, is to find their point of intersection. So their points of intersection, it's going to occur when the two graphs equal each other. So 2 on 3x plus 2 equals x minus 1 squared plus 1. And let's go. Let's move the 1 and expand. So that'll be plus 1. X. So just moved him over there. I'll also expand this. That's x squared minus 2x plus 1. 0 equals x squared. What's minus 2 on 3? Minus 8 on 3. Oh. I've got another term because it's plus 1. Sick. Okay, so now I can just go x outside of x minus 8 on 3. 0. That means x equals 0. Nice, that was this. And also equals 8 on 3. Okay, so this value here is 8 on 3. I just don't need to know what the y coordinate is, do I? Okay, so I just need to integrate between x equals 0 and x equals 8 on 3. Let me make sure that's right, so I don't want to go much further if that's wrong. Yeah, okay. Okay, so I need to integrate this between, between 0 and 8 on 3. Move that. So move this a bit higher. Okay, 0, 8 on 3. Let's, God, I've got to expand that again. Okay, 2 on 3x plus 2. Just going to be really careful here. X squared minus 2x plus 1 plus 1. Two on 3x plus 2 minus x squared plus 2x minus 2 dx. Okay. 2 plus 2 on 3. Did I do that before? Yeah, 8 on 3. Okay, so 8 on 3x plus 2 minus 2. Cool, they're gone. Minus x squared. Okay, this is equal. Do I want to make another column? I can't be bothered. Integral. Raise it. Divide by it. Raise it. Divide by it. Between 0 and 8 on 3. That's equal to. Okay. 8 on 6. 8 on 3 squared minus 1 on, my god, this is an insane question. Minus, oh look at that, 0. Yeah. Can I type all that into the calc? Oh, I got something, do I have something different? Oh no, they just simplified the 8 on 6. Okay, so when you type that into the calculator, you get 256 on 81 units squared. 3 marks. Whew. I'd say your first one would go to this, your second one would go to setting this up correctly based on your picture, and the third one would probably be a solution. I say this every time I do a question like this. They're the same every single time. This question, you can almost guarantee you're going to be asked it. It's so... it's always exactly the same. It's hilarious. And they give you the answer a lot of the time. Alright, so... they take out a reducing balance loan. So I remember this lesson. It was an online lesson, so there's a video for it. And it's always exactly the same. I've done it in every paper that I've gone through. The loan has an interest rate of that compounded per month. Okay, so let's adjust the rate. The rate's going to be 4.8% divided by 12, which is equal to 0.4. Oh, would you look at that? 0.4%, which is... I need to be careful. I'm going to run out of room very quickly. Which is 0.004. Oh, I wonder where that 0.4 above came from. What else we got? Equal monthly installments of $3,000. We're going to use a sequence. Just gotta be careful. Used to find the amount owing after n repayments. Okay, this is the key. At the end of each month. Okay, so at the end of each month, that means at the very start, so at A0, before anything's even happened, she takes out a loan of this. So this is how much money she owes. And after the first month, it gets compounded. So 550,000. The interest rate occurs on it, 1.004. So that gets added on. And then she makes a repayment. So take away, makes the 3151 repayment. Okay, that's it. So then after the second month, she's got whatever the first month was, so you just leave that, don't work that out. After the first month, it gets, so let's write it like this. It compounds again, so this is in here, and then 3151 gets taken out. So A1 was equal to all that stuff above, so 550, Pat should have left more lines for this, oops-a-daisy. Minus 3151. Okay, so that's A1. Then that gets compounded. And then 3151 gets taken out. So all I did was replace A1 with all of this. I can simplify this. So when you, like this whole bracket is times by this. So I'm going to go boom, boom. Now when I go boom, this makes a 2 there. So I'm going to go 550,000,1004 to back 2 minus 3151 1. So that's my second one, 51. Then I'll factorize that. It's just a lot of writing for these marks, but it's the same every time, eh? So 3151 outside of 1.004 plus 1. Okay. Now that gets compounded a third time. Oh no, I'm gonna run out of room. Oh well. So A2 gets compounded, and then 3151 comes out. A2 was all that. 550. 1.004 squared minus 3151. 1.004 plus 1. Big bracket. Gets compounded. Then 3151 gets taken out. Let's move this. Oh my goodness. You can go here. There. Okay, this is equal to. So I'm distributing this bad boy. He's going to go there, which makes that a 3. And then he's going to go here, which makes that a 2. And that a 1.04. And then this comes out. 550. 1.004 cubed minus 3151. 1.004 squared plus 1.004 minus 3151. And I can factorize that 3151, and I write a 3 there. So I'm thinking about it. My mic better be on. I'll check. Jeez, that's bright. Just look at my face in the thing. 1.0043 minus 151. 1.004 squared plus 1.004 plus 1 as required. Yo. So that's that line. Oh, that's backwards. Look, that doesn't matter. I'm not going to reduce marks for that. Wow, really earned that 2 marks. Now, find the expression for AN by using a geometric series. So normally at this point you'd say, okay, I know what the pattern is, A3, power of 3, and then this goes up to 2. So then I'll just write the general one. So AN is going to be 550,000. So this to the power of N minus 3151. And then I'll write backwards, 1 plus 1.004 plus 1.0042 plus, and it goes all the way up to 1 minus what I want. So, God, I'm running out of room. So it goes up to 1.004, 1 less, so n minus 1. Okay, that's different. I don't think I've done that before. Okay, what am I asked to do? And finds the number of years to pay off the loan. Oh, that's a good question. So if I were to pay off the loan, so it's paid when I no longer have any money to owe. So when the amount owing is 0. So I'm going to set this thing equal to 0. I'm just copying and pasting this. Copy. Whoa, it crashed. It was that big. Cool. Did it copy? No, it didn't. Please don't crash again. That equals 0. Follow Drew. Now, this thing is a GP. So it's a GP where A is equal to 1 and R is equal to 1.0. I swear I've done this question 1,000 times. So I must write it identically. So, sum, how many terms are there? There's n terms, because it goes from 1 to n minus 1, if that made any sense. So 0 to n minus 1. There's n terms, so then it's A outside of R minus 1. 1.0 minus 1. Okay, so that's equal to, wow, this is going to be disgusting. 1.004 n minus 1 on 0.004. That's right. I'm surprised I didn't see anything. Okay, so that means 0 equals, so going back to this line. 5. sure in the HSE they don't make you write on these. So I'm just going to replace all of this with this. You might be asking, why am I doing this? Well, the goal is to find n. We want to know how long it takes for the loan to be paid off, so we're looking for n. You'll notice that n is stuck in stuck in two places. Okay, so let's move this boy over here so it becomes a positive. So 3151 outside of 1.00. There's a reason I haven't distributed that 3151 yet. It's because I want to be able to divide by it, hopefully. Oh my god. Alright. I'm going to do this divided by this. It's disgusting. It's not nice. Okay, and then I'm going to times by this at the same time. Okay, that's a semi-decently nice number. So what happened? This went and this went, so the only things left over here are 1.004 and minus 1 equals... So this ended up being 22003151. So again, I divided by this, so I went over that, and then I times by this. Okay. Now I've got 1. Okay, now I'm thinking divide by, God, I'm running out of room, divide by that. So, oh, surely not. Is there a better way of doing that? Yeah, no, I'm going to have to, okay, so minus 1 equals this. This is disgusting. Is this normally how gross they get? I don't think they normally get this gross. My apologies. Minus. Okay, then I can factorize that. So 1.004 and outside of 22003151 minus 1. Yep. Then I've got to divide by it. Jesus Christ, I have no room for this. Blink. So then, okay. This is going to go over here, which means I have to divide, but I'm going to divide by this fraction and stuff. So I'm going to flip this and flip this. So, and there's going to be a minus out front. So 3151 on 2200. What do I do with that minus 1? Let's just do it properly for a second. Minus 1 on 22. It doesn't matter how disgusting it is. At the end of the day, you've got to type it into the calculator. Okay, minus. Let's just. Let's take the log of both sides. So. I can't take the log of the negative. Can I? Can I just get that? Put it there. Ln. All this. Equals, I'll bring the n out front, say n ln, and then I'll divide by it. So ln minus 1 on 2200 on 3151 minus 1 on ln. Look, the more discussing the better, yeah? Okay, then you type that into the calculator, and you're not getting around 300. Okay, Now, it's asked for the nearest year. These are in months, because it's month repayments, 300 months, and that's around about 300 divided by 12. It's around about 25 years. Oh, you really earned 5 marks for that, eh? What do solutions look like? Yeah, I think there was a way better way of doing that. And it would have been here. Here. Just times that and then divide this and move everything to one side. Is that? Yeah, actually, it would have been here. I already had everything on one side. So I should have just times this. I should have just figured out what this divided by this was, simplified that, distributed it, factorized these, and then it would have been alright. Oh well. But being... Oh well, who cares? No, it's done now. Okay, the probability density function of the normal distribution is this thing. So I think I've shown you this before, but it's pretty disgusting. It's the reason we use the table, because we don't want to have to integrate this every time. The adult wingspan of Ingalls species is... Okay, so you'll notice that this is a blank formula, and I've got a mean and a standard deviation, and here I've got a standard deviation, and a mean. So I can input my stuff into this. It says use a trapezoidal rule. Now, this, on the surface level, looks like a pretty mean question, but it's actually not. It just... You just need to... What was I going to say? Just need to take care, I guess. Take real care. Alright, so the function is 1 on... The standard deviation is 12, so 12 root 2 pi e to the minus x minus... Now, the mean is 180 squared on 2 times 12 squared. 2 times 144 is 288. I can just put 288 down here. Okay, that's my function. Now, the trapezoidal rule is, now, probability of randomly selecting one adult member of the species and finding its wingspan to be between 150 and 165. Okay, so mean of 180, deviation of 12. Alright, sorry, I was just trying to think of what this thing might look like. So I'm going to draw it. Our mean's 180, and we're trying to find the probability between 150 and 165. So pretend this thing looks like this. We're trying to find this, well, one application of the trapezoidal rule. Okay. Yeah, right. Now, it says one application, and it's only given us one, like, width. So essentially, we're trying to find this area. Now, the trapezoidal rule, so the area of the trapezium is around about, because it's only one application, it's only one width. Estimate or overestimate. Okay. It's going to be the it's the height or the width. So height on 2, and it's just derivative of the first. No, sorry, the distance of the first, distance of the last. That's like the most basic form of the trapezoidal rule, because normally what you've got. This question appears hard because it's giving you less information, but normally what you've got is you've got a bunch of function values, and then you try and find trapeziums, and then you do like this one plus 2 times these. But this one has only given us one trapezium, so I've only got this height and this height. So this height here is going to be f of 150, and this height here is going to be f of 165. Yeah, and this here is going to be h. So that equals. this is going to be 15 of 2. Okay, now this is the part where you've got to be disgusting and type things into your calculator. So f of 150 is going to be f of whatever this is. So you're going to have to put it into here. So it's going to be f of 150. Why did I put a minus there? It's definitely a plus. Yeah, what am I doing? Because it's trapezium, because the formula for a trapezium is like half a plus b h or something. I don't know why I wrote a minus. Anyway, and then f of 165. So that's going to be 15 on 2. Do I want to do that myself? Not really, eh? 0.00146 plus 0.01522. It's round about equal to 0.125. Okay. And again, the area under the curve of a probability distribution function will give you a probability. So that means a probability of selecting a random angle with a wingspan between 150 and 165 is around about 0.125. So like an eighth, 1 in 8 chance. Anyway, what a weird question. That's only weird because, yeah, anyway. Okay, is the approximate probability found in part A an estimate or an underestimate or an overestimate? That's a good question. Okay, so because we've used the trapezoidal rule, there's kind of a clever way of doing this. You can think about how far. I don't have a table, do I? No, it's not. Okay. My picture's a little bit misleading here, but if you think about this, it's a normal distribution. So the graph of a normal distribution looks like that. So if I'm looking at these 2 points, which is 150 and 165, and then I try and draw a trapezium on it, it's going to go over it. So it's an overestimate. Whoops. That's disgusting. It's an overestimate as the normal curve. You can see that it's concave down. It's concave down. And any trapezium drawn, just trying to explain my way out of it. Even if you just drew a picture, I'd be pretty happy with that. So, in other words, this thing's concave down, so no matter what 2 points I'm going to draw, my line's going to be on top of it. For those 2 values, because obviously if it was like these 2, it would be an underestimate. So for these 2, anyway, hope that kind of makes sense. Where's concave up? Did I say not concave down? Okay, I've drawn this picture terribly. It's like that. Sorry. Should have said concave up. I was just drawing that, I was like, hang on, that doesn't make any sense. So if it was between these 2 points, see how it's concave down, obviously you're going to have an underestimate, but when it kind of tails off like this, it'll be an overestimate. Anyway. Okay, I feel like this is a pretty mean question. Oh well. Domain, x can't be 0. So that means from everything from negative infinity, open bracket, to 0, open bracket, union, 0 to infinity. So I just can't have 0. Either or, you can use either of these, but there's normal notation, there's set notation. Differentiate. Great. Show that the derivative is that. Okay, so f dash x is 2x plus, so that's plus x to the minus 1, so that's minus x to the minus 2, which is 2x minus 1 on x squared. So 2x, let me do this, 2x times x squared on x squared minus 1 on x squared. That is 2x3 minus 1 on x squared. Done. Find and determine the nature of any stationary points. Okay, so I've got to set that equal to 0. Set the first derivative equal to 0. So that's 2x cubed minus 1 on x squared equal to 0. We only care when the top is equal to 0. So 2x cubed minus 1 has to be equal to 0. X cubed has to be equal to 1 on 2. That means x equals the cube root of 1 on 2. We have for that? What is that? Nothing nice. Okay. Each point should include a y coordinate. Wow, okay. Wow, this is 5 marks. There's not enough lines for this. Anyway, okay, so a y coordinate. Y equals, what was the function? X squared. X squared. Oh, plus 1 on. Jeez. Cube. Okay. Oh, that's going to be really gross. Are we leaving that? I'll leave it as. They've done it as. Yeah, okay. So it's stationary. I'm just looking at that, like it's the coordinate, the cube root of a half, and the y coordinate, cube root of a half squared plus 1 on the cube, like, just looks weird. So if you type all that into the calculator, that's 0.8, so this is 0.8, around about, and this is around about 1.9. Okay, there's my only stationary point by the looks of it, because I only got one solution for my first derivative. Okay, points of inflection. So do I want to differentiate that again? Let's go use the quotient rule. Okay. I want to rewrite this. 2x, so forget this for a second. 2x cubed on x squared. Actually, no, I want to leave it. I want to differentiate it again. So I'm going to use this form. So the second derivative is equal to 2x, so that's just 2 plus derivative of this, so I drop it, so that's going to be a plus 2x to the minus 3. Plus 2x to the minus 3, plus 2x to the minus 3. So that's 2 plus 2 on x cubed. Okay, now I set that equal to 0. So 2 on x cubed equals minus 2. 2 equals minus 2x cubed. Minus 1 equals x cubed. X equals minus 1. Okay. Then y equals 1 squared plus 1 on 1. 2. So that's a point of inflection. So point of inflection at minus 1, 2. Okay. God damn, there's not enough room for this. This is why I asked for spare paper, people. Oh, I didn't even determine the nature of that first one. Okay. Let's get rid of that line that I just drew because it's annoying. So I'll put that in the second derivative. So f double dash of Oh, that's cool. So they cancel. Greater than 0 means it's concave up. Therefore, can concave up, which implies a minimum. This is a weird graph because it was an asymptote as well. Alright, I've got everything. I've determined the nature of my stationary points and I've found points of inflection. Okay, is that everything I want? I feel like I've done this wrong. Point of inflection minus x equals -1. So that's, oh, -1. Oh, so that's 1 minus 1 is 0. So that's going to be 0. Alright, 5 marks there. By considering the domain, the parts of its domain where it's increasing and decreasing, and the behavior as it approaches infinity and negative infinity, sketch this bloody thing. Include x-intercepts, asymptotes, stationary points, and... yeah, okay. These are fun. I reckon these are fun questions. They're just, yep. Alright, let's just include everything I've got. I've got a stationary point at 0.8 and 1.9. So 0.8, let's call that there, 1 point, let's call it there. So 0.8, 1.9. And it was a concave up, so it looks like that. That's kind of weird looking. What else? I've got a point of inflection at -1, 0. So -1, 0. So here, there's a point of inflection. I haven't tested either side of it. Damn it, I should probably do that. Okay, point of inflection. So I can check the gradient. So the first derivative at, so just before it, so at -2. The gradient at -2. Or maybe I want the concavity. I'll check the concavity at -2. So that's going to be, where's the second derivative? Yeah, it's here. So 2 plus 2 on -8. What's that? That's positive. That's greater than 0. So then, might just check a little bit. So minus 0.9. That's 2 plus 2 on minus 0.9. That's going to be, that'll be 2 plus 2 on. That's negative. So that's less than 0. So that means the concavity is like this here and like that there. Okay, that's interesting. What strange. Oh, there's an asymptote. It's an asymptote at x equals 0. So asymptote at x equals 0. Okay. Now, as x approaches infinity, what happens? So x squared plus 1 on x. Y, which equals x squared plus 1 on x, approaches, so I just chuck a massive number in there. So like 999 squared plus 1 on 999. That's a huge number, so that approaches infinity. So that's just going to go off to infinity, goodbye. Okay, now as x approaches 0 from the positive side, so from the positive side, y equals, no, y approaches, so I just go something really close to 0 on this side, so 0.001. So 0.001 squared plus 1 on 0.001. Okay, that gave me 1,000. So that's also approaching infinity. So that means it's just going off to infinity. But it will never touch 0. Okay, so I've got a kind of a parabola there. Now, as x approaches 0 from the other side, what happens to y? So from the negative side, so I'm going to do negative 0.001, so heaps close to that side. So I'm looking at what happens when x is like here. Y is massively down there. Okay, so y approaches negative infinity. So then this just goes off to negative infinity. Goodbye. Okay, and as x approaches negative infinity, y approaches, so if I just put a massive number, negative 999 squared, negative 999 squared plus 1 on negative 999, that's a massive number, so this just goes off, goodbye, to infinity. That's the point 0.01. What at x? No, it's a 0.10, you idiot. No, minus 10, God. There aren't any other x-intercepts. What else did it want? Asymptotes, it's got it. Stationary points, it's got it. Points of inflection, it's got it. Done. That's a very strange looking graph. But nonetheless, it's a graph. Alright, we're up to the last question. What's the time? 41 minutes. That's not too bad. And guess what? It's a max minimum question. Alright, consider a rectangle inscribed in a circle, centered at the origin, with radius 5. Okay, that's just explaining the question to me. Find expression for the area of the circle in terms of x. Okay, so I'm not told that much. I know what the equation of a circle is. It's x squared plus y squared equals r squared, or 25. Find an expression for the area of the circle. Right, that's fine. Area of the circle in terms of x. Okay, so you normally just consider both shapes. So area of circle is what implies this. Can't really say equals. So let's rewrite that in terms of y. So y equals plus or minus the square root of 25 minus x squared. Okay, and then the area of the rectangle is what's that gonna be? I don't know, do I? Yes, I do. Hang on a minute. What's this length? 1, 2, actually, let's just count it. 1, 2, 3, 4. So this is 8. And then this height, 1, 2, 3, 1, 2, 3, so that's 6. Okay. Oh, but it depends. I don't know what I was doing there. That depends on my x and y values. Okay. I'm not told what this x and y value is, so I can't comment on that. But what I do know is that this, let me just draw stuff. This is going to be the length x, and this is going to be the height y. So that means this whole length here is 2x, and this whole length here is 2y. So that means the area is going to be 2x, 2y. We happy with that? Okay. So that's 4xy. Now I want the area of the circle, so I want this to only be in terms of x. Do the rectangle in terms of x. Oh, that's so interesting. The solutions say the area of a rectangle, but that says the area of the circle. What's the next one say? Yeah, the dimensions of the inscribed rectangle. Okay, this question's written wrong. Damn! Oh, that's meant to be rectangle. That's not good. God damn it. Because then you just go 4x, and I already know what y is, it's all of this. So square root of 25, and use the positive because we're looking at an area, and that's your 2 marks. Uh-oh. That's not good. Well, that last question is going to be a stitch up for anyone that attempts it. Oh well. Because you're not given enough information to find, because, yeah, okay. Anyway, find the dimensions of the rectangle such that it has the maximum possible area. So the area of the rectangle needs to be maximized. So that means I want to find the derivative of the area of the rectangle with respect to x. So that means I'm differentiating that thing. So I'm going to use u and v. So vu plus uv. Okay, v is this junk times the derivative of u, which is 4, plus u, and then the derivative of that thing. So that's the same as to the. Let me rewrite that. So the half comes out the front. I times by the derivative, and then I've got to drop the power. Okay. Okay, I've got a lot of things that are going to cancel here. That goes and that goes. So then I've just got minus x, but then I've got that 4 there, so that's going to be minus 4x squared on root 25 minus x squared. Okay, cool. Now, it's a maximum when x equals 0, when the derivative equals 0. So, yeah, right, eh? Let's move that over. So 4x squared on 25. Okay, in doing that, I can divide both sides by 4, so that can go and that can go. And then I can times that bottom part up, so then I've just got x squared equals that squared. So then x squared equals 25 minus x squared, so that means 2x squared equals 25. It means x squared equals 25 on 2, which means x equals plus or minus 5 on root 2. Okay. I've got to show that it's a maximum. My point is in the positive quadrant, so then I only need to take, x has to be greater than 0, so I have to take the 5 on root 2 value. Do I want to differentiate that again? I don't really want to differentiate that again. Okay, so nature. If you don't want to have to differentiate the thing twice to determine its nature, just check a point either side. So what have I got? 5 on root 2, that's 0. And then I want, so this is the first derivative. What's 5 on root 2? 3.5. So let's check left and right of that. So left, 0, right, 4. So if I put 0 into my first derivative, which is this, if I put a 0 in there, that's going to be 0. So that's 4 times 5. That whole thing is going to be 0, so that's going to be positive. And then if I put a 4 in there, that'd be positive, that'd be positive, that'll be massive, so then it's going to be negative. So because it changes gradient, so it goes from that to that, it's therefore a maximum. So you can see that the graph will go like that. Therefore maximum, show that, find the dimensions. Oh, I've still got to find the dimensions of the rectangle. The maximum possible area. Okay. Therefore, dimensions are. Oh, I've got to find the y value. There is not enough room for this. Okay. X equals 5 on root 2. Y equals. Where's my function? 4x outside of. Okay, this equals 4 on, no, 20 on root 2. That's 25 minus 25 on 2. Do I want to leave that? Let's just leave that exact. Can I leave that exact? Yeah. I'm not simplifying that. Surely they don't want me to simplify that. They haven't. They've also got it wrong. Where's their 4 gone? Yeah, right. The solutions are whack, eh? Damn, I need that simplified though. Y equals. You've got an expression for A. An expression. Let me just simplify this. That is 25 and 2. Root 25 on 2 is what? That's just 5 on root 2. I don't really get what's going on because in this solution, this kind of just disappears, and then they're saying the maximum area is a square, which would make sense, but I don't know what happens to this 4x. It's 20 times 5, 100, so that's 100 on 2, which is 50. I don't know about this question. 54 minutes. I think this whole question's buggered. Consider me a confusion. All 5 roots. I don't know. Everything else is fine until. I don't know. Most of the questions are alright. It's a little bit of a hard test, maybe. We'll see. I'm curious how people go. I remember that last one. Oh. just disappears. Okay, let's not let this go on for more than an hour. So yeah, I think we're good.